Thank you very much for attending this session. This talk is about building the course of operations management around a web-based simulation game. The approach that I propose is not for R1 business schools or even R2 business schools. It is more appropriate for teaching-focused business schools, which form about 42% of the business schools accredited by AACSB. Indeed, it is appropriate even for a subset of these teaching-focused business schools, which I refer to them as state-funded teaching-focused business schools. These are schools with non-traditional first-generation students from a diverse population with a large coefficient of variations in their knowledge, skills, and abilities, who also work 20 to 60 hours per week. This is the process flow in prototype of this type of undergraduate programs. About 65% of the students are community college transfers and 35% are first-time freshmen. Out of that 65% transfer students, about 50% get graduated and about 15% dropout. Out of 35% first-time freshman students, about 20% get graduated. In total, about 70% of incoming students get graduated and the rest, the majority of them drop out, but a small portion also just add to the population of these institutions. Therefore, the question is, from a system point of view, what we can do to improve this situation. Where is the binding constraint? Is it the professors, course material? Is it the course delivery system? Is it the administrators? Where is the binding constraint? If we look at this process, a student plays three roles. First, they are our customers. Therefore, we need to make them happy. But more important than being customers, they are products. And therefore, we need to produce good product in four-dimensional space of cost, quality, time, and variety. Performance of state-funded teaching-focused business school in cost dimension is excellent, while their tuitions have been increased by 10 times, still they are the cheapest institution for undergraduate study. But on time to degree, which is the flow time as we just discussed, and it is about 6.5 years, performance is quite low. As a product of this system, we need to improve cost, time, quality, and variety. But more than being a customer or being a product, students are precious resources of this system, and without their significant presence, this system cannot succeed. I have discussed presence in four dimensions: physical presence, the time that the student spend on his or her education on campus or anywhere out of campus. Mental presence, which is the level of focus and concentration during physical presence. Collaborative presence, the willingness of a student to work with his teammates and go through a process of collaborative learning in satellite micro campuses with his or her classmates. Please bear in mind that given the progresses in biotech, this student may live for 100 years. given the progresses in infotech, they may need to reinvent themselves every 7 to 10 years. Professors and tutors will not be there to help them to reinvent themselves. They have themselves and the network of friends and colleagues that they have developed over their education and career. And that is why collaborative presence is third dimension of this presence. And the fourth dimension is indeed lack of presence, the distance of the student from depression and anxiety. We need to have perform good in this four dimensions. So the first day of classes is not really about the syllabus, but it is about teamwork and collaborative learning. I have learned if the teaching material is linked with real life, or at least with virtual life, the students are willing to have better presence. And that is why I first incorporated game in my course. And now I am developing the course around the game. The game by itself forms 20% of the grade. This was before, but when it was 20%, we had a lot of free riders who would have trust on decisions that the three others, the two other, or a single person in their team would have made, and they would have not spent much time on the game. But gradually, I replaced the examples and problems of the class with examples and problems from the game, and incorporated the game material into quizzes and exams. And therefore, the weight of the game in the overall composition of marks is much more than 20%, and we have better contribution. This is the interface of the game. In this course, I have really benefited from these three books. And I need to acknowledge the knowledge that these three books have delivered to me. This is the interface of the game. Demand come in. We have the demand. If capacity exists, if here we have capacity, demand comes in. If we have inventory, then it comes into the production process. Demand is here. If CONWIP allows, if the maximum number of loads within the system allows, it comes in. If inventory is there, then it will go into shop floor. Go to the first station, then second station, third station, back to the second station, and out. When we click on orders, it will give us job arrivals. We can click here, plot job arrival. We have the job arrivals. We can click here and we can download data. And this is data. Now we have data for about 50 days. This is 50 days before the game starts. And we can apply 1 period moving average, 2 period moving average, all period moving average. We can also prepare some descriptive statistics. We can learn a little bit about Excel graphs for different types of moving average. We can compute basic metrics like MAD, MSE, and MAPE. As I said, if this was only for the game, contributors would have learned the material and we have contributed in the game, but free riders not. However, now, because we have quizzes and exams around this material, beside the 20% which they collect for the game, then more students participate. This is one of the examples of the quizzes that I have built and I have uploaded into Canvas. For example, there are about 26 quizzes of this type configurable on different Excel sheets. Excel sheet could have 40 to 60 lines. They download it, quizzes and exams, and everything is all behind computer. Students have Excel at their full disposal and no proctoring system. Compute forecast for the next period using 7-period moving average. Compute math for the last period. And compute the standard deviation of forecast next period. And compute tracking signal for the next period. And MSE for the next period. And the standard deviation of forecast for next period using MSE. So these are things that we may do regarding applying moving average to the game. Before going further, let me explain a couple of words about how do I generate quizzes. This topic is not about time series analysis, it's about process flow analysis. So I show this material, I teach it. Processes, we do have process time. For waiting lines, we have number of flow units, number of people, number of patients in each waiting line, and then based on that we compute flow time of different type of patient throughout the system and also average number of patient inside the system. Then I take this example that I have solved in class into an Excel sheet and I generate, say, 26 different versions of it. Each row of this Excel sheet is a problem. And then I apply a macro and build something like this. And here, this is an Excel sheet, 26 problems of this type, along with their questions are listed over there. Now I need to turn this one into something readable for Canvas. For example, I need to turn it into a Word file. But if I copy an Excel file like this, into a Word file, there will be thousands of spaces over there. And unfortunately, these are not the same kind of spaces. In other words, I cannot say replace space by space and then continue for say 5 minutes, 10 minutes, and everything is done. No, taking out the spaces at my level of skills may take 1 day. So what I did, I realized LaTeX doesn't know the difference between 1 space and 10 space or whatever tabs. So I take this file, copy it into a LaTeX file, then I create a PDF file out of that LaTeX file, then I export that PDF file to a Word file, and I get something like this. This still needs some edits. I do those edits, then I'm able to upload it into Canvas and generate, say, 26 problem similar to this, where I have the problem statement here, and then I have maybe 10 questions. This is multiple choice problem. We have a problem, and then we have 10 multiple choice questions about that problem. This is how quizzes are generated in my course. Let's go back to time series analysis. We developed moving average around the data in the game. Now we can also do it for exponential smoothing, compute tracking signal, compute math, draw them, and so on and so forth. Then we can use solver to find optimal alpha for exponential smoothing, and we can draw it. And we also learn how to use data table to find the optimal alpha up to as many as decimal points. And then we discuss that these curves, MAD, MAP, MSE, are not a type that they come down and go up. They may trap into local optima, and therefore it is possible that solver find this one or this one as optimal solution, while the optimal solution is here. Solver cannot find this, but data table can find it. Therefore, I have generated a lot of problems out of them. I have realized in which one of them Excel is trapped in local optimals, and then I have created a set of quiz in which a student must show that they have learned data table because by using solver they cannot find the optimal solution. This is an example, exponential smoothing. We give them a specific alpha, they forecast for the next period. Then we ask them to compute math based on that alpha for the next period. And then we ask them to compute standard deviation of forecast for the next period based on the math they have computed. Again, student download a Excel sheet of say 40 to 50 to 60 rows and compute best alpha up to 3 decimal points. We also apply regression. We use regression to find the intercept and slope for the data that we have downloaded for the game. We again use solver to find optimal intercept and optimal slope, just as an example of implementing solver. Okay, now we are done with predictive analytics or with time series analysis, regression, and association. Now let's go and explore another topic within the game, and that is process flow analysis and the Liddell's law. I click on this icon and I get the data for customer orders. I click on this icon and I get completed jobs. And I plot it and then I download it. So now incoming orders and completed contracts. I can compute inventory and flow time based on these two sets of data. This is input, this is output. For 50 days, I use the simple beginning ending inventory. Beginning inventory plus input minus output is equal to ending inventory. And I copy it down. I can also prepare a descriptive statistic for this data, but I usually do not use analysis tool pack in Excel. I just use Excel functions. I think Excel functions prepare students better for additional computations that they need. So we compute these metrics first to have some understanding of the situation. Now I have average input, average output, and average inventory. Liddell's law is correct for anywhere if inventory in the system is equal between those 2 points. But we don't get involved in that much details. Just we apply it and we say, okay, this is input, this is output. You get one of them, for example, output as throughput, or you compute the average of them as throughput, whatever you like, and then you have inventory. If I get output as throughput, and average inventory is here, therefore, flow time is equal to inventory divided by throughput. And because throughput is per day, flow time also is day, and then we can multiply it by 24 to get hour. The system works 24-hour day. And then we go inside each station and we look for queue over there. These are the waiting line over a period of 50 days. As we can see, this was kits in the inventory, but now it looks better. These are the arrivals. These are completed jobs. And these are queues in different stations. And this is day 49. And this is day 50. These are the number of kits in each waiting line at each station. These are in terms of kits. Each contract composes of 60 kits. Therefore, if I divide these numbers by 60, I will get number of contracts that are waiting in each of these stations. And therefore, the total number of contracts inside the system is close to 6, and throughput now is about 5. Therefore, if I divide inventory by throughput, I get flow time, which is slightly above 1. And then I can repeat this computation for each of the 3 stations and get these. And obviously, because inventory is here more than anywhere else, therefore, here is the bottleneck, station 2. So that was a little bit about flow time. Now we can go to another topic, which is capacity. This is customer order, that is completed jobs. These are the machines in different stations. These are stations, 3 stations, input, output. This is input data. This is output data. And these are utilization in different stations. Utilization is station 1, station 2, station 3. So beside the information that I had, I also have some information about utilizations at different stations. And if I do have the throughput and those utilizations, I can estimate the capacity of each station. Completed job, if I go and compute the average for the previous table or the last day, this is the throughput. We have only one machine at each station. Utilization of station 1, utilization of station 2, utilization of station 3. And I have manufacturing this data for the teaching purpose because I didn't want to go through a lot of decimal points. So I have made utilizations in a way that capacities come out as reasonable numbers without too many decimal points. Therefore, if I divide throughput by utilization in the first station, I get capacity of 8. For the second station, I get capacity of 6. And for the third station, I get capacity of 10, even without going inside capacities. And just by looking at the number of orders that are waiting in front of each of these stations, we realize that bottleneck is here. And now our utilization computations confirm that understanding. A chain is as strong as its weakest link, and because here this is our weakest link, our process is only as strong as that one. And then I create a quiz based on this topic and based on the previous topic to let the student to make sure that they have understood the descriptive statistics, process flow analysis, and capacity planning. This is a problem. Again, they download data, for example, for 40 to 60 days. They have input, output, and they have utilizations. Similar to the table we had, compute coefficient of variation for orders arrived, compute the range divided by median for the completed orders, compute average inventory, compute average flow time, compute average utilization of station 1, compute the capacity of station 1, compute the capacity of station 2. So it will give them a good review of the material that I have taught on descriptive statistics, on Little's law, and on capacity. Because we do have capacity, and because we have one machine, therefore we can compute the unit load of each machine, the activity time at each machine. Now, demand is here, capacity is here. and the weakest is 6. If we allow more than 6 to come in, flow time will exceed 1 day. We need to put a barrier here. And if demand is more than 6 per day, we should not allow it to come in. And the student by practice will learn it that if utilization is equal to 1, waiting line will go up. Therefore, perhaps the students will bring this limit to 5. But because we also have variability and the student may lose some orders, they need to play with it to fine tune it. Of course, if minimal lead time for delivering the product instead of 1 was changed to 2, then we had 2 times 6 equal to 12 as our barrier here. If it was 3, then we have 18 here as our upper bound for number of flow units inside the system. So now we have this situation. We have 1 machine in each station. Capacity of the bottleneck is 6. Process capacity is 6. Demand is 16. Implied utilization is 2.67, which is above 1. Utilization of different stations are here. Now we go and increase the capacity of bottleneck and change this one to 2. Another station becomes the bottleneck. We discussed with the student that we double the capacity of the bottleneck, but the capacity of the process did not get doubled, did not go from 6 to 8 because bottleneck shifted from this resource pool to another resource pool. Now capacity is 8, implied utilization is 2, and the most utilized station is not a station 2, but a station 1. Bottleneck here is a station 1, and therefore we increase its capacity. We go from 1 machine to 2 machine. Capacity goes to 16. Bottleneck shifts here. Implied utilization is 1.6. Still, demand is above capacity. We double the capacity of station 3. Capacity of the process goes to 12. Implied utilization still above 1. And then we continue here where capacity is equal to demand. But capacity equal to demand leads to high waiting lines, and that will push us to go beyond the lower bound due date that we have. And therefore, while we complete the products, we may don't earn anything, and indeed, because we spent $600 on each product, on the raw material, we produce the product, but we may lose $600 on each product we sell. Therefore, we increase the capacity. Now the capacity of the bottleneck is 89%. Maybe we think 89% is still a high utilization rate, and therefore we may increase the capacity by 1 more machine. Therefore, from 111, we now are in 342. We purchased 6 machines. An average price of each machine is about $100,000. So we spent $600,000. But for that $600,000, our production went from 6, maximum of 6, to 16. So we produce 10 more products per day. And if, for example, we have a contract which give us 1,250, if we have a contract which give us, say, 1,000, and a contract which give us 750, if we purchase the raw material for 600, if we go from 6 and 750 to 16 and 1250, for each unit of product, we earn $500 more, and we produce 10 additional products. So we can go from 6 to 16, and from sales price of 750 to 1,250. Therefore, for this 6, we can make $500 more. And for the rest, for this 10, we can make 1,250, but the cost is 600. Therefore, that would be 650. I have 6,500 and I have 3,000, and therefore I can make $9,500 more per day. If each machine is 95,000, and if I make additional $9,500 profit per day, I need 10 days to recover for one machine. And if I buy those 6 machines, I need 60 days. The game has 50 first days, which we have already passed it. 7 times 24 plus 50, that is 218. But we need to pay 60 days as a payback period for those 6 machines. So I have 158. And if I multiply by 9,500, I can make a lot of profit. So I shouldn't stay with 6 capacity at first contract 750. I should try to go up. But it is not easy. It is not just capacity. Here is what we computed before. This is the number of kits at the waiting line of each station. That is the number of contracts in front of me. Therefore, 5.93, as we computed before, are waiting inside the waiting lines. And if throughput is 5, therefore, it takes 1.19 days. But now we want to look at the problem from a different side. Here we looked at it from the point of view of the Liddell's law. Let's also look at it from the point of view of utilization, which is throughput divided by capacity. If we go through the utilization data, we realize that utilization in 3 stations are these numbers. And because we only have one machine, therefore this machine on average is with 0.62 flow units, with 1 flow unit, and with 0.91 flow units. If I add them together, it is 2.53 flow units, which is inside this system on the average. And because that 5 is the throughput, if I go through this formula, throughput divided by utilization will give me capacity. Therefore, I can compute capacity of different stations as we did it before. And if I divide 24 by capacity, I get this flow time. And if I add them up, this is flow time. This is theoretical flow time, which these flow units spend inside the processes. I can find this 0.056 also by dividing the average inventory by throughput. I can again find this one. So this is theoretical flow time, and this is flow time in the waiting lines, waiting line flow time. If I add these two together, I will get flow time, which is the time with processors plus the time inside the waiting line. We have capacity either 6 or 16, but we need to regulate the relationship between capacity and maximum allowable number of load inside the system, which we show it by max WIP. We use max WIP or CONWIP to estimate average inventory, and we use capacity to estimate throughput. Then we divide CONWIP by capacity to estimate flow time. Here in this situation, we see a team which has not performed very good. At the beginning, demand was low, therefore utilization in 3 stations were low, and therefore flow time was low, and therefore they were able to make all the potential revenue, which is $1,000 in this case. But as demand goes up, demand was low here, now it has gone up. Therefore, utilizations have gone up in these stations, and therefore waiting line has gone up. And because waiting line has gone up, the flow time also has gone up, and therefore the company was not able to deliver the product before the lower bound, and therefore the revenue gradually has come down and it has reached zero. Right now, this company is producing product, but it's selling it for $0, don't earn anything. However, they have spent $600 to purchase raw material. For this company, utilizations were low here. Utilization were low here. Utilization were low here. And therefore, waiting lines were short, and therefore they were making maximum revenue. But gradually, demand goes up. Gradually, demand goes up. Utilizations go to about 100%. Waiting line goes up. Flow time goes up. And revenue comes down, goes to zero. And they know that they need to reduce the flow time, and therefore they need to reduce CONWIP. But they have reduced CONWIP a lot, more than what they needed. Because right now, this is their lead time, and lead time is about half a day, 0.6 day. They can increase their CONWIP and bring their flow time up to here and produce more. This team, they are earning full revenue. Demand goes up. When demand goes up, their flow time increases and their revenue comes down. This is their flow time, leading to this reduction in revenue. They don't make any action, but they are lucky because demand is going down, and while they have not made any action, their revenue goes up to maximum. So there are two things. First, select appropriate capacity, then regulate flow time, which is regulated through R times T equal to I, by estimating throughput and average inventory using capacity and CONWIP or MaxWIP. Now we go to inventory. Jobs arrive, jobs are completed, we know the utilizations, we have inventory. Here is demand over time. It is going up and down around something. We can look at these data, we can estimate. So demand is like this, but at some point we don't allow all the demand come in, we allow this much, and we reject the difference. We covered moving average. We covered exponential smoothing and regression and association. We covered process flow analysis and Little's law. We covered capacity planning, and we covered flow time and CONWIP. Let's go to inventory. We have job arrivals here. We have completed jobs here. We have utilizations here. And we now can plot inventory over the period of time. And usually this period of time starts with the first 50 days of the game. This is a picture of demand. At least in this 84 days, it is stable. But because there is a maximum number of loads inside the system and we do not allow all of them to come in, we have lost some demand, which have reached to a point when the number of loads inside the system reach the maximum allowable here. This is average inventory inside the system, and this is throughput. So as we can see, this one is 6-7 times of this one, and therefore, if we are under any contract which its due date is less than 7 days, perhaps we are losing money. This is one analysis we do with the students, and then we go to an interesting curve which shows cumulative input versus cumulative output. And then we realize that the vertical gap between these two cumulative curves is inventory, and horizontal gap between them is flow time. So this is also a pictorial representation to understand the relationship between throughput, inventory, and flow time. We tell the student that the physical cost of inventory is 10%. For financial cost of inventory, sometimes we tell them it is 10%, and sometimes we leave it to the student to compute it, and computation is not difficult because they can download cache, they can download cache data. This is the cache throughout the first 50 days. They can download the Excel sheet, they can plot it, and then they may get the starting and ending cache as average inventory divided by 2, or they may do a regression and then get the first point and last point and divide by 2, or they may just average all points. They have average cash and they have interest that they have earned during this period. By dividing them by each other, they can estimate that the interest rate is very close to 10%. Physical cost 10%, financial cost 10%, but what about obsolescence cost? Obsolescence cost becomes a very important issue by the end of the game, not during the game. We teach basic EOQ model by using the game data. I mean, exactly we go through the game, we look around as I computed the carrying cost, ordering cost is given, and then we discuss what is the best strategy, how much should we order each time, and then we discuss average inventory, where if you don't have safety stock throughout the year, the average inventory is equal to half of the maximum inventory, and then we plot that for different order size, and then we go through through Excel sheet for the ordering cost, and then draw the Excel sheet, and then also write the equation, and then we add these two curves together, and we tell the student that it has been proved that the optimal solution is at the intersection of these two curves. Of course, the student can see it by adding those two, and they realize it is when those two are equate, and therefore that is one way to prove EOQ model. We said at EOQ, ordering cost and carrying cost are equal. The only unknown is Q, therefore solve it for EQ. And that is one way to help the student not to memorize EOQ formula, but to be able to understand it, not based on derivative because they can't, but based on this simple equation. Student tell, oh, this game is over there for 286 days. Why do you compute for 1 year? The answer is it doesn't matter. If you want to compute demand for 286 days, then H is not what you have computed. HT is not 20% of the purchase price, and purchase price is 60 kits, and each kit is $10. Therefore, in that case, carrying cost is not 20% of $600, which is $120, but you should multiply by 286 and divide it by 265. Then we go through this EOQ formula and assume that demand is for 1 month, and therefore inventory carrying cost is 1/12 of what we have put over there. And then we also assume demand is demand for 1 day, but we need to fix the carrying cost for 1 day, and we see all formulas reach to the same result. Therefore, we tell the student you can assume demand over any period as long as you also compute carrying cost, unit carrying cost for the same period. We also have the opportunity to discuss a little bit periodic inventory. Say if instead of EOQ, you decide to order every 30 days, what will happen? What is the relationship between ordering costs, carrying costs, and so on and so forth? Because all of them happen inside the game, therefore, I think a student grasps it easier. Then we go to ROP, we download the data, and we realize that at the beginning of the game, the reorder point is set up in a way that indeed we let the student first go through it. After we pass, say, 100 days, then we go there and discuss that. Here, conclusion is we place an order too late when inventory level has come down. Therefore, we need order at a higher point. Because the difficulty with being out of inventory is this. If I'm out of inventory and if I have already reached maximum CONWIP, it doesn't matter. I can manage it. But if I don't have inventory and it leads to delivery time to exceed, then I not only lose my profit, but also I have paid $600 for raw material. And if I am delivered it after the upper bound for delivery, I earn nothing. So I lose both profit and also the cost of the raw material. So we have the data, we have average and standard deviation. We a little bit talk about what is the difference between when the lead time is fixed and demand per day is variable compared to when demand per day is fixed and lead time is variable. We show some graphs and then we try to show them what is the difference between those formulas. And then we come out and say, okay, what is it? How much inventory should we have? And then we discuss overage costs and underage costs. In the game, price could be $750, depends on the nature of the contract, $1,000, $1,250. Cost is $600. Underage cost compared to overage cost is quite high. Therefore, we go for a very high service level, sometimes maybe 99% or more. When we define that here there are two forces, one force push us order more and order more, one force tell us order less and order less. Where we stand depends on the relative force of these two forces, which is force to the right divided by summation of the two force, which defines the red area. And after defining the red area, finding the point for that red area is just a formula in Excel. But at the end of the game, before the last 50 days of the game, students become disabled to make any change. If they have less than what they need, for some days at the end of the game, they will not be able to deliver any other order. In that case, they may lose 150, 400, or 650. But if they have extra material, they have what they have purchased, it doesn't worth anything by the end of the game. So underage cost is 600 compared to overage cost, which is 150, 400, or 650. At best, service level is something around 50%, but usually even less than 50%. And that is how we discuss end of the game story. And this is the situation that they have by the end of the game. This company always was carrying extra inventory. That is the case for the end of the game. At the end of the game, they have had some extra inventory. This company performed not bad, a little bit short, but at the end of the game, they have come out with extra inventory and they have lost whatever they have paid for that. This company was always short a little bit, but at the end of the game, it is too high. They lose a lot of money for that remaining inventory at the end of the game. This team was always short. At the end of the game, it's also short. This team was always short. At the end of the game, they are a little bit overstock. This team has performed perfect. During the game, they have not lost anything. They were a little bit overstock, maybe 5, 10, 20. So that is 20 times 120, 2,000, 3,000, the cost of this. But at the end of the game, they have performed perfect. Thank you very much for paying attention to my talk. I really appreciate it.